Uh, okay. Hello all. Thank you for joining us today. And it is a great pleasure today to welcome Dr. Lianghao Cao from California Institute of Technology to speak to us about derivative-informed operator learning with applications to cost-efficient Bayesian inversion. So he is a postdoctoral scholar research associate from the Department of Computing and Mathematical Sciences at Caltech. He obtained a BS in engineering mechanics from UIUC and a PhD in computational science, engineering, and mathematics from the University of Texas at Austin. His research blends mechanistic modeling, uncertainty quantification, and scientific machine learning to understand, enhance, and control the quality, validity, and reliability of simulation-based predictions of complex physical systems. It's a great pleasure to have you with us today, and please take it away. Yeah.
Thank you. Thank you so much for the introduction and invite. Um, so, um, so I guess we have 45 minutes in total. I'm going to try to stay at the beginning of the talk a little bit. You can think of this as a tutorial, and probably going to rush through some numerical results toward the end. But hopefully, my goal today is to introduce you to the method of derivative-informed operator learning. Um, After the talk today, my hope is that you could go and implement this on your own without having too much trouble. Hopefully during any part of the talk, if you have a question, you can just ask. But if you want to ask toward the end, that's okay. So let me know if you have trouble hearing me or any other technical difficulties on your end. Okay.
Understood.
Okay, great. So, all right. Let me see. All right, so this work is something I've been working on for 2 years. And the main driving force is collaborators at University of Texas at Austin. So Tom Mullery is the main contributor behind all of these works, and Professor Omar Gattas. So I'm going to cover a lot of ground today, but a lot of work ongoing. I'm only going to cover a little bit. So mostly I'm going to talk about the learning formulation, which is in the first paper published in 2023 by Tom O'Leary. And I'm going to touch on, the use of this learning methods to accelerate geometric MCMC and surrogate-driven measure transport. And during the talk, I'm going to cover three projects which are driven by a PhD student at UT Austin. And they have presented their work at different conferences, but the work is not published yet. I was just talking like these are my contributors. The contributor to the work I'm going to talk about, especially these three works that's ongoing, I'm going to cover a little bit driven by students at UT Austin. And the top three work I'm going to cover most. These are works done by me and Tom O'Leary in the span of 2 years. And I'm very excited to share that with you. All right, so I'm going to talk about a little bit motivation upfront and a introduction to this supervised learning method we call derivative informed learning. And then we're going to dive into some technicalities, how would you implement these in practice? And we're going to use it to build surrogate models that can be used to accelerate geometric MCMC and accelerate measure transport for solving Bayesian inverse problems. Okay, so let's start with the motivation. So the idea is all about, it's all around predictive computational science. So the setting is where we have a computational model that predicts some quantity of interest that we care about a physical system. And this computational model takes an input of, let's say, initial condition, boundary condition, constituent parameters, and also a decision variable. It contains control, design, actions. And with this computational model, which is usually differential equations derived from physical laws, we predict some observable things that we observe in experiments. We want to predict performance and failure metric and etc. So of course, we don't want to stop just there. The parameters, we don't know it up front, right? We have some prior belief of what a parameter is. It's described by this distribution mu. And we want to also make optimal decisions based on the computational model. We want to optimize our outcome by maximizing some reward function given this decision variable and uncertain parameters. So this whole process, we call it outer loop problem. We wrapped around the computational model in this loop of optimization problem where we have to constantly, repeatedly evaluate the computational model at new inputs. So the two tasks I'm really interested about are parameter inference, or later we're going to call it Bayesian inverse problems, and the right optimal control under uncertainties. These two problems are very difficult if the computational models are very expensive um, to evaluate. Large-scale PDE models may be entirely nonlinear or time-dependent. It's also very difficult when the input parameter that we want to infer and optimize are very high dimensional. So it may be a spatially varying or temporally varying function as parameters, or the decision variables are also very high dimensional where there are many actions you could do at a given time. So it's even more difficult due to the fact that we now have a distribution of a quantity of interest, and one might be interested in the tail probability of that quantity of interest. And in the context of digital twins, one may even want to do real-time inference and control. So these difficulties stacked together make this problem really interesting. And there's a lot of research going on in this area. So the perspective. So let me just give you an example that I'm working on with with some folks at UT, especially by student Marshall. Um, so this example is a joint inference of the earthquake slip and rigidity variation of the Earth from co-seismic deformation. So what we see on the left here is a map mesh over near Japan, and we know that Japan is a country where a lot of earthquake happen nearby. So in this work, what we're trying to do is to take the observation from GPS station, which are oranges in orange color here, take the data from this GPS station that records the deformation of the Earth to infer jointly where and how the earthquake happened, which is the slip, and the variation of the rigidity of the Earth, which is the shear modulus field um, around Japan. So in this problem, we input a slip condition and shear modulus field as input to our PDE model, which is linear elasticity. We solve using finite element. We obtain a displacement field, which is about uh, which at the courses level is about 2 million degree of freedom. And then we extract a model predicted observations at the GPS station. So we extracted that model predicted deformation, and we try to infer the unknown parameters from the observation data. So our goal is to move on from deterministic inverse problem, which has been solved quite well and led to many impactful publication listed here. Um, our goal is to do it under uncertainty so that we could assess the risk and make risk-aware decisions based on these inferred results. So this problem is, of course, very computational intensive. If we do it a naive way, one four problem could take 30 minutes to solve. And because we're inferring entire field, the parameter are really high dimensional. At the courses level, we have to deal with at least 6K uh, dimensional parameters. And even though it's a linear PDE model, the inverse problem is nonlinear. So the posterior cannot has relatively complex shape. We have to infer that shape from data, and that requires to repeatedly evaluate the PDE model. So very difficult. So so what can we do with these problems? So a very simple and very powerful way to do this is simply find a so-called surrogate model of your model, a computational model. So we in the offline phase, we'll generate some input-output response of your computational model G, and we train a parameterized function g tilde uh, to emulate the behavior of this computational model. And on the online phase, we either directly replace the high fidelity computational model with the trained surrogate model, or we could use them with the high fidelity computational model in a multi-fidelity setting. So some important consideration for surrogate, the use of surrogate in this setting are what I believe are two. One is customization. We need to design a surrogate architecture and training that leads to accurate solution of the outer loop problem. So we need to target the surrogate for the outer loop problem. And the second is efficiency. Now we cannot invest, let's say, 10,000 PD solve in some settings. If the model is just too expensive for us to spend that much computational power into the surrogate construction itself. So the ideal situation is that we could train a really good surrogate model with very few evaluation of G. So this align with so-called science per joule vision that's been around in the HPC community. Okay, so the theme of this talk is we're going to talk about a particular surrogate construction methodology called derivative-informed neural surrogates. And we're going to use it in solving Bayesian inverse problem, just like the example that I showed you. Um, so in Bayesian inverse problem, the quantity of interest is the observables, the quantity that we're observing experiments. We want to use model to predict that. And use the predicted quantity, we try to sample or approximate the posterior mu of y. Y is the data, using the Bayes rule. So that requires to use methods like MCMC or variational inference that requires to evaluate a posterior density. And each evaluation requires to solve the Forer model. So it can take up millions and tens of millions of PD solve to be able to do this. And we want to accelerate this process using a very cost-efficient surrogate model. All right. So now I'm going to cover introduction to derivative-informed supervised learning. So let me start with a very simple example, which is the conventional supervised learning. So this is something I believe everybody now understand and know how to implement in practice. The first step of conventional supervised learning is data generation. So let's say we have the input, parameter input M, and we want to collect the model prediction Q first by randomly sample the input and then evaluate your computational model, solve the differential equation that you have to collect the quantity of interest. And in the training phase, we have, let's say, a neural network model or Gaussian process or any kind of emulators, and we minimize the loss function by matching the surrogate prediction with the data at the given input. So this is an empirical risk minimization problem over samples. Now, a little bit of notation, I use script M as parameter space and script Q as the space of quantity of interest. And the notation here means that we're evaluating norm in the space of the quantity of interest. So let's say if Q is in the Euclidean space, and this will be Euclidean norm. If Q is some functions, then this will be the appropriate function norm. Okay. So if let's assume we have an infinite access to infinite number of samples, in that case, this average term becomes an expectation. The expectation is over the distribution of the parameter that we sample from for the data set, right? And this expectation can be written as a norm. This norm is for the norm on the Bachner space, L2 mu. So recall that the space L2 mu is essentially a weighting, a mu-weighted Bachner norm of nonlinear map from the space of parameter to the QI. So an example, let's assume we take the Euclidean space as our input and output. And let's assume the measure mu, the probability distribution mu, have a density pi. Then the L2 mu norm measure of error is essentially matching the difference, the L2 norm of the difference of your two function that you're measuring error on, weighted by this density function averaged over the entire input space. Okay, so very intuitive. Uh, so now the question is, if we have this particular infinite sample limit then measured by a norm, then well, it opens the door of, trying more complicated norm or maybe a stricter norm. So this is what we consider here. The question that we ask is, how about we just control the error of your surrogate approximation in a stricter norm? So here we consider mu weighted H1 solvable space comes with a solvable norm. So what does that space mean? So H1 mu contains function that belongs to the H2 mu function, the square integrable function, like we seen just now. And we also require the Fréchet derivative to be a Hilbert-Schmidt operator, and meaning that in the sense that this particular norm, H1 norm, is smaller than infinity. So here's some notation. The notation D here denotes the Fréchet derivative, and HS denotes the space of Hilbert-Schmidt operator with this norm right here. And of course, because of this additional derivative term, this norm is stricter. The error control is stricter. And I want to mention that when M is a function space and mu is Gaussian, this particular space needs special treatment, but we're not going to cover it here. So let me give you an example again. So in the Euclidean space, this particular mu-weighted H1 solvable space norm becomes essentially a finite dimensional solvable space norm where we, instead of, in addition to the mismatch in the function itself, we also measure the mismatch in the derivative or Jacobian of the function. Okay. So, all right, so let's consider just simply replacing the norm in the loss function using H1 mu norm. So if we do that, then we obtain this sort of enhanced norm, an enhanced loss function with additional derivative error term measuring the Hilbert-Schmidt norm. So if we take the same route as we did in the conventional supervised learning, the first step would be discretizing E by first generating Monte Carlo samples, input, output, and derivative samples. And during the training, we do an empirical risk minimization, but not only over the input-output sample, but also over the sample of the derivative. So this formula is very natural if we consider switching from the H2 mu in function approximation to H1 mu function approximation. So let me give you a very simple example. So let's say we are in 1D. M here is 1D, and it's assigned the function that we seek to learn, g of m, is a sine function. In this case, the derivative is cosine. So in the setting of derivative informed learning, we will match, let's say, a neural network output with both samples of G and samples of DG. In the conventional learning, we only will be matching G. Okay, so let's train the neural network using 18 randomly sampled points on the unit domain, and let's see what happens. So if you see on the right, with conventional training, you see overfitting at the low sample size regime quite severely. Now, and if you look at how the conventional training the conventionally trained neural network approximate the derivative, you can see that it's pretty terrible and it has small oscillations. Now, if we switch to derivative informed training, we see that overshooting and undershooting becomes less severe. So better generalization in approximating the function g itself, but also we see a much better improvement, much better improvement in approximating the derivative itself. So the error dropped almost in half by introducing the derivative in the training procedure. Okay, so that's great. This seems to be a promising way to approximate a function that we can generate derivative data from. And we've seen the promise of these training methods, which is that it prevents overfitting and it seems to perform well at a low sample regime. Now, there's still a bunch of questions that we need to answer, which is in the setting of a real life, let's say a very complicated computational model. How do we realize this training method in practice? So this is what we're going to talk about next. How do we build a derivative-informed neural operator surrogates using this derivative-informed learning methods? All right, so I will go back again to the big picture. So on the left, we have Bayesian inverse problem, which is driven by computational model G. For the purpose of this talk, we think of this G as composed of an observation operator that extract observables from the model predicted state and parameter. And F is our PD solution operator. We have a PD model as our computational model, and it takes in some input parameter and output a solution of the PD. Okay, so and the surrogate model seeks to approximate this particular G. So how do we use the derivative-informed learning method to approximate or to construct this surrogate model? So first, let me just go to the conclusion up front. So, there's what I believe there's two reasons why people want to use derivative-informed learning over conventional learning methods. The first is that from what we observed, in many cases, the derivative-informed learning is much more sample efficient for surrogate construction. If you look on the left, this is a typical curve you will see when you plot the testing error of a surrogate training results. The y-axis is prediction error. The x-axis is construction cost. The construction cost contains mostly data generation costs because for large-scale model, it may take days or even weeks to generate data. And we want the model to perform well in the sense that it gives lower prediction error at low construction cost. And derivative-informed learning is able to give us the better efficiency on this spectrum. Second, derivative-informed learning enhance the performance of the outer loop solvers. We directly control the error in the Fauché derivative, which these Fauché derivative is going to be used to evaluate the gradient and Hessian of the outer loop algorithm. A good example here is geometric MCMC, where what you're looking at here is a distribution in the background, and we're using the Fauché derivative of your computational model to place a proposal distribution that's shaped like the local curvature of this distribution. Now, you need a very good approximation of the Fauché derivative to be able to predict this local geometry. And derivative-informed learning is able to give us that. So I hope to show you why these two are true by going through the house. Now, looking at this loss function, there's several questions that we need to address to actually implement this. First of all, is given a PD model, how do we generate the Fauché derivative samples? And the second question is, we have this Hilbert-Schmidt norm here, and how do we evaluate a Hilbert-Schmidt norm when M and Q, let's say, are function spaces? And how do we handle the size of the Fauché derivative because it is an operator, linear operator, from a very high dimensional space to possibly another very high dimensional space. So let me just cover the number one house, the evaluating the Fauché derivatives. So so the approach that we take here is through uh, differentiating models via essentially sensitivity equations. Now, I know that there's a lot of well-established library out there that use differential programming to extract this information. And I'm not going to cover that here, but you could also use that as a mean to generate Fauché derivative samples. Here we consider a particular case where we can use sensitivity equations. This particular case is that the PD solution that we model here can be explicitly written as a implicit function. So what I mean by that, right? So let's say U, it belongs to the space of a script U, and we have a residual function that we use to solve the PD, right? We know the PD is solved when the residual evaluate at the state U and the parameter M is equal to 0. So this now is written as in a way that F is an implicit function. F have to satisfy this relationship at every input M, and we can invoke implicit function theorem to differentiate F. So how do we do it? So here is a very quick glimpse into two ways of doing this differentiation. So on the left, we have so-called forward sensitivity. So we use the action of the Fauché derivative to form the Fauché derivative operator. So let's say we have a variation of dm, then what we need is to solve a linear forward sensitivity equation given by the derivative of the residual with respect to the state and derivative of the residual with respect to the parameter. So this is the linear forward sensitivity equation. On the right, what we see here is adjoint sensitivity equation. We're probing the Fauché derivative by its adjoint. So that involves inputting a variation in your output quantity of interest and return a variation in the parameter. Now, this approach requires us to solve so-called linear adjoint sensitivity equations. So one thing I want to notice now is that these equations, this is where inversions, this is the left-hand side, and this is the right-hand side. These equations only depends on U and M, right, on the left-hand side. So that means a given PD solution and the parameter input, we are solving repeatedly the input variation using the same PD left-hand side. So different right-hand side, the same left-hand side. And we'll see later on that it leads to drastic cost reduction if we design the use of solver carefully. So let me just give you an example. So here we consider a nonlinear reaction diffusion with an uncertain parameter field, a log diffusivity field, and we have a cubic reaction term. And this PD model is driven by boundaries. On the top is 1, on the bottom is 0. And with some random input, we solve PD, and we use the PD equation to extract pointwise observations as our quantity of interest. So for this particular example, the way we can extract the Fauché derivative by its adjoint action is to solve an adjoint PD of this form. So let's assume we have a variation on the quantity of interest is given by 1 in one of the entries and 0 in all other entries. So first, we'll use the observation to map it back, adjoint of the observation operator to map it back to the state space. So what we see here is result of that operation. You can see a little impulse response here where the observation is flagged. And then we solve the adjoint PD equation to obtain this particular adjoint state, P. And with the adjoint adjoint state P, we plug it into this Laplacian term, and then we'll obtain a variation in the parameter. So this procedure give us the variation in the parameter given by a variation in the observables constrained by our computational model. Okay. So of course that's great. However, to form the entire derivative, we need to do the solve repeatedly for, in this case, 25 different input. So how does that make sense? It sounds very expensive to solve. So it turns out that it's not quite so. Because this is a nonlinear PDE, we need to use some sort of iterative method to solve this, to solve the nonlinear PDE. And one evaluation of the computational model G takes about 0.075 seconds. Now, if we form the entire Jacobian derivative using linear adjoint sensitivity solve 25 times, it takes totally 0.024 seconds, so about 1/3 the cost. So the trick is actually to use the direct solver and reuse the factorization where the left-hand side of your sensitivity equation stays the same and the right-hand side changes according to the input variation. So this cost saving can be quite extreme in some cases. Let me show you two examples. So on the left, we have hyperelastic deformation. So the input here is the Young's modulus of your material sample. It's a spatially varying Young's modulus. And the output is some measurements of your displacement field. In this particular example, we use Neo-Hookean material. And on average, over the input, it takes 8 Newton step for each forward solve. And in this case, the evaluation time of the computational model is about 1.1 seconds. To form the Fichet derivative, it only takes about 0.13 seconds. So it's, in this case, it's much cheaper to collect the Fichet derivative sample than evaluate the formal model at a new sample. So it's a question of whether we want to sample a new position or extract the Fichet derivative at the current position. And the answer is definitely yes for forming the Fichet derivative in this case. On the right, we're looking at linear elasticity model of co-seismic deformation. So this is a big linear PDE. And it turns out that because the PDE is linear, the adjoint sensitivity equation has the exact same left-hand side as the forward model. So if we use a direct solver to solve the forward problem, then we can directly reuse the factorization of the forward solve to form the Fichet derivative. In this case, because the state is extremely high, very high dimensional, the difference can be very extreme. So the forward model evaluation, if done in parallel across 16 cores, it takes about 1.6 minutes. But the probing the derivative action only takes about 0.27 seconds. Very extreme. So in these two type of cases, highly nonlinear PDE and linear PDE with high dimensional discretized states, it's much cheaper to form Jacobian than evaluate a formal model at a new sample. So in these cases, derivative informed learning makes a lot of sense. Okay, the second question I want to answer is evaluating Hilbert-Schmidt norm. And this can be a little bit technical. So, so the idea is that the Hilbert-Schmidt operator, when M or Q's are functions, can be transformed to a matrix as the space of matrix with Frobenius norm. So how do we do it? So the trick is we need to find a set of orthonormal bases on the input and output space. And with that orthonormal matrix, we can find an isometric isomorphism by probing the Fichet derivative along the direction of the bases. So if we probe it using the derivative action, then we get so-called the Jacobian matrix by columns. And if we probe it by the adjoint action, then we get the Jacobian matrix by rows. And once we form this matrix, J, the Hilbert-Schmidt operator can be evaluated by the Frobenius norm. So it's very natural because we've seen that in finite dimensions, this is already true. Okay, so the third question I want to answer is how do we deal with the size of Fichet derivatives? So with this procedure I laid out before, we're going to generate a so-called Jacobian matrix representation or Jacobian representation of the derivative that has the dimension of dq times dm. And as the example that we've seen for the earthquake, dm can be uh, several thousand dimension, and this matrix stands. So definitely not tractable if you want to deal with the entire Jacobian matrix. So what we want to do is we want to find a very efficient way and very cost accuracy aware way to reduce this Jacobian to a latent space RQ and RM. This very naturally leads to an architecture of the G tilde surrogate using reduced spaces parameterization. And if we reduce it to a latent space, then we also have a relatively low training cost and manageable memory burden. So of course, there are many literature out there about reduced basis neural network or reduced basis neural operators when M, OQ are functions. So the question that one need to ask in this case is, how do we actually pick the reduced basis? So again, recall that we have DQ basis on the output and DM basis on input. How do we arrange the basis so that we can pick a top RQ and DRM basis? So a lot of work has been focusing on using proper orthogonal decomposition or principal component analysis. Basically, you take a sample of input and sample of output and do a single value decomposition or eigenvalue decomposition separately. So also there's a strain of work that focuses on using the Fauché derivative samples to compute these reduced bases. And the second approach makes a lot of sense for us because we're already generating Fauché derivative samples. And it turns out that for the purpose of learning a surrogate model and for the purpose of Bayesian inverse problem, the derivative informed basis, or we call it derivative informed subspace, they use Fauché derivative samples to generate these reduced bases. This method is much, in terms of error bounds, are much more superior than purely sample-based dimension reduction. We're going to talk about a little bit later on. Okay, so now we arrive at our first surrogate model architecture. So this architecture is inspired by the fact that we're reducing the Jacobian by reduced bases. Now, since we're already reducing the Jacobian, why don't we reduce the entire architecture so that the training can be done in the latent space only? So this is really the motivation of the reduced basis derivative informed neural operator. So on the left, we have encoder that we stacked the basis on the input by that to form the encoder. And what it does is encode a very high dimensional input into a latent space of dimension DRM. And we'll use a very simple feed-forward neural network to parameterize the mapping from the reduced input to the reduced output. And on the output side, we'll use the output decoder, which is the basis function stacked, to decode the output, the neural network output, to the full space of quantity of interest. And it turns out that with a combination of how we evaluate the Hilbert-Schmidt norm using the derivative and how the architecture is constructed, we can formulate the H1 mu derivative informed operator learning fully in latent space by pre-projecting the data. So here we're looking at exactly the same training loss function, but with data projected into the latent space. And we're directly training the backbones of this surrogate model, which is the neural network. So the training becomes very efficient and very fast. Okay, I want to go back to the dimension reduction and show you some interesting result. So like I mentioned, derivative informed dimension reduction is very attractive to us because we already have the Fauché derivative sample. So how do we find these basis function using Fauché derivative? So the way we do it is to solve a generalized eigenvalue problem using the Fauché derivative samples. Now, a little bit of notation. Sigma n here, we assume come from some belief in the data, in the observables. This is actually given by the additive Gaussian noise in the Bayesian inverse problem. It signifies how much we trust certain data or not. On the right, we have the prior covariance for the Gaussian prior for inverse problem. And as you can see, we build in the information of Bayesian inverse problem into this eigenvalue problem. And this expectation in practice is discretized by sample, and we solve an eigenvalue problem based on samples. So here's a result that show you that this dimension reduction is optimal in the following sense for Bayesian inversion. So let's assume that we have approximate posterior given by replacing the competition model in Bayesian inverse problem using surrogate. And the error bound says that the expected difference between the surrogate approximate posterior and the true posterior, or the high fidelity posterior, on average over the expected data distribution, we don't know the data yet. We collect data after training. So on expectation, meaning that on the expected range of data, this expectation is bounded directly by the sum of trailing eigenvalue that we choose to truncate. So we can pick bases based on the eigenvalue decay of that we obtain by the solving this generalized eigenvalue problem. And we have additional term, which is the L2 mu error of your neural network matching so-called the optimally reduced G, which is a conditional expectation. So this is a very nice bound because there's no constant in front. You can estimate this using samples. And this bound is this bound compared to, let's say, PCA or POD, this bound is provably lower than the bounds for PCA and POD.
I have a question.
Yes.
Do you have bounds for, like, say, the map values of the approximate and the true distribution or the mean? Because I think that's what we care about more rather than the distribution itself.
Okay, so for the map and the mean, you're talking about a point estimation. So I'm sure these can be so I'm not sure if one really cares about the mean or the covariance because here is a nonlinear inverse problem. The posterior is not gonna look very non-Gaussian. So now I could imagine you could get a bound for the mean. Yes. So here we have a bound for the distribution itself. Now you just need to take an expectation with respect to this distribution. So I believe it can be done, but I haven't looked at it yet.
Okay, thank you.
Yeah. All right. So here's an example for the informed subspace that we found for the nonlinear reaction diffusion problem. So on the top here, you're looking at the decoder rows. So these are the ones that we do in the product with the coefficient to get out to decode. And on the bottom, what you're looking at encoder columns. The encoder columns are the one that we use to in the product with the parameter field M to map to the reduced basis. You can see that the encoders contains information of the output. So this is in some sense unique feature if we use sensitivity information of the model. Okay, here's a learning result. What you see here on the left is reduced basis DINO and approximation error in the competition model itself. And on the right is the error in the prediction of Fauché derivative. As you can see that the derivative informed learning is much superior in learning the computational model itself, but also much superior in learning the Fauché derivative. This we're looking at about 16 to 60 time cost reduction. Now I just want to show you that we're counting essentially the cost of data generation on the x-axis. So you see a little bit of shift in these data points. This is because we are accounting for the data generation of the Fauché derivative in addition to the input-output samples. Okay, a similar problem, hyperelasticity deformation, we're looking at similar behavior as well. the derivative-informed learning is much more cost efficient than a conventional learning. Okay, so I want to go through real quick some ongoing work. So in here, we're looking at derivative-informed Fourier neural operator. And we try to train the Fourier neural operator using derivative-informed formulation. And here in this work, we derived or we proved a universal approximation of a derivative, meaning that on a compact set K, there exists a FNO and any tolerance such that we can find an FO that approximates the computational model arbitrarily well, as well as derivative. So derivative approximation is the new result. So for the Helmholtz equation that we tested out using the derivative-informed training formulation, we see that at the same data generation cost, the FNO training is much more accurate using derivative-informed formulation. Now, Helmholtz is a very difficult problem. As you can see that even with a lot of data generation costs, we can only get to about 90%. So here's an ongoing work with going beyond H1. So we're using HK derivative learning formulation to learn the surrogate model. And having additional second derivative information in the training, we're seeing an improvement in both the input-output, the derivative, and also the second-order derivative accuracy in the surrogate model. All right, let me maybe spend a couple minutes going real quick through some of these applications to Bayesian inverse problems. So the first application that we're interested in is accelerating geometric MCMC. So the idea of geometric MCMC again is to use the local geometry information given by the Fichet derivative of your computational model as a way to propose MCMC moves. And the problem with these methods is that if we use the full computational model to do it, we gain a lot of efficiency measured by the effective sample size of the resulting sampling. But the computational cost is much more. In fact, the sampling efficiency that we get by using so-called the moving Hessian, at each point we place a Hessian at the sample that we're at right now, so-called moving Hessian, the efficiency gain that we have is offset by the cost. So the efficiency per computational cost, we don't really see any improvement compared to, let's say, just fix a posterior geometry approximation and generate the entire Markov chain with a fixed Hessian approximation. So how do we go about solving this problem? So we use the surrogate model that we trained using the derivative-informed formulation to propose to make proposal moves. So in this case, we use so-called simplified manifold metropolis adjusted long-driven proposal, where there's a bunch of derivative and function evaluations, model evaluations. And we mix it with a multi-fidelity algorithm where it still targets the true posterior, but now use the surrogate as a mean to construct proposal. So the result that you're looking at here on the left is, first of all, the result what you're looking at here is a distribution of the effective sample size over all the degree of freedoms of the parameter. We are looking at a parameter field for the nonlinear reaction diffusion problem. So on the left are the effective sample size distribution for the surrogate-driven geometric MCMC trained with conventional formulation. Very inefficient. It's even worse than the proposal given by the prior, which does not adapt to the local geometry. Now, using the DINO formulation, the surrogate-driven geometric MCMC sees great improvement in the effective sample size. The quality of the Markov chain that we generate is very high. And we can see that as we increase the number of data, it goes towards the ground truth, which is the moving Hessian manifold model. And I just want to show you real quick about speed up results. So if we account for the offline training cost in computing the speed up, we will let's say, the model-driven methods, PCN, which is prior-driven, and MALA is model-driven geometric MCMC. we let them run first while the surrogates generated data and training. Well, in this case, the data generation cost compared to the number of effective sample size is only about 10 when compared to MMALA, 10 to 67. So the investment into surrogate is worthwhile as long as you collect more than 10 effective samples. And asymptotically, we're seeing speed up against the prior-based sampling methods about over 50 times, and against geometric MCMC over 8 times. All right, let me cover real quick amortized variational inference. So the idea is that we want to train a transform map on the parameter space, which could be infinite dimensional, via minimizing the distance of the push forward of the prior by this map and the posterior. So the trained transform map, after this minimization, will produce approximate posterior sample by evaluation. So our approach here is to integrate the design of so-called lazy map and reduced basis DINO, where we consider this reduced basis architecture using derivative informed subspace, and the transport only acts nonlinearly in the subspace of in the derivative informed subspace and does nothing in the kernel, which it will let the prior fills in. So now what we do here is we replace where the computational model is located with a surrogate and only the backbone of the surrogate, which is the latent neural network. And we do this training via stochastic optimization of this reduced objective function in the latent space. And this requires us to evaluate the Jacobian of the neural network. And because we use derivative informed training, the accuracy is really high for the Jacobian. So this training actually is much more feasible with derivative informed learning. So how do we amortize the cost? Well, we essentially invest all the computational costs into the offline surrogate construction, which is also only performed once. In the online phase, when we collect data, repeat the procedure for the transform map training, and then we can produce posterior samples. And this training can be done rapidly because we no longer have to touch any computational model. And using GPUs, we can essentially train this transform map in seconds. So here's an example. We're looking at 4 instances of Bayesian inverse problem with synthetic data sampled from the prior distribution of our hyperrealistic deformation model. And we'll see how different variational inference methods perform over these range of Bayesian inverse problems. So here we're looking at posterior approximation results. We're seeing diagnostic divergence or reverse KL divergence, effective sample size percentage, forward KL divergence, and map estimation error. And the blue curve is LazyDINO, driven by DINO surrogates. The orange curve is LazyDINO, driven by surrogate trained by the conventional supervised learning methods. And the purple here is very interesting. It is the usual normalizing flow, flow matching, formulation where we using input-output sample only to train the transform map. So using the same number of training samples, we see that the LazyDINO is much, much more superior. In particular, it reached almost 50% effective sample percentage asymptotically. Very impressive result. So here's some posterior visualization. We're looking at the leading modes of derivative informed subspace. So as you can see that this posterior distribution is relatively nonlinear. And if you place a Laplace approximation on the top, which is a Gaussian approximation, it does a relatively poor job. At 250 sample, LazyDINO is already matching the posterior quite well. And we see incremental performance after 2K and 16K. So if we consider conventional training methods, we see that they drastically overestimate uncertainties at low training sample size. The reason is the surrogate accuracy is not good. While we can see that LazyDINO is already matching the true posterior very well. Eventually, as the training sample size increases, this conventional surrogate does catch up. Now, the interesting case is purely sample-driven amortized simulation-based inference method. As you can see that even at 16 sample is still drastically overestimating the posterior. So definitely not a very efficient method. Drastically less efficient than LazyDINO. All right. Conclusion. So I hope I've shown you the promise of this method, which is theory-informed operator learning of neural surrogates. The essence is that we exert error control in H1 mu space, the solvable space, and the surrogate, due to this formulation, is learned using joint sample of model input, output, and Frechet derivative. And this formulation leads to high accuracy at low construction cost. The result that we're seeing shows that we're looking at 16 to 32 times or more cost reduction in learning the map itself, the model itself, and 30 times to more than 100 times cost reduction for learning the Frechet derivatives. And one of the key tricks in enabling this derivative learning is dimension reductions. And we've shown briefly how DINO surrogate can be used to enable fast and accurate solutions of Bayesian inverse problems. And we've seen over 50 times and 8 times speed up against prior-based sampling methods in geometric MCMC. And we also shown you LazyDINO methods, which integrates a structure exploring transform map, lazy map, with the surrogate, and we achieved more than 100 times efficiency in amortized Bayesian inverse problem than purely sample-driven methods. And this is only a glimpse into many ongoing literatures on this topic. We also have optimal control, experiment design, and hopefully many more to come. Okay, thank you for attention, and I'm happy to take any question.
Excellent, the speaker. Thank you. That was a very informative and very engaging talk. I think we can open up the floor to questions first in the room and also online as well. People can type in the chat or unmute themselves and ask.
Yeah, a quick question for the for the MCMC sampling, when you the transport map, like how do you maintain some sort of invertibility there, and how do you do so? Like what sort of architecture did you use?
So the architecture we use is, I believe, is masked autoregressive flow
I see.
for this case. So it is still the usual architecture you will use for transport, but the training is different. This is a model-driven training using reverse KL divergence. So the usual amortized inference setting, people use forward KL divergence with samples. The reason people do that is they can avoid evaluation of likelihood. But in our case, it plays to our favor because we have a surrogate model for fast likelihood evaluation. So this is the architecture that we use.
Oh, thanks.
A quick question regarding the Frechet derivatives. So just out of curiosity, firstly, are there any applications where you would also potentially be interested in even higher order derivatives for surrogate training?
Yes.
Okay.
Yes. Sorry. Yeah. So to answer that question, so it depends on really your outer loop algorithm. If your outer loop algorithm requires Hessians, let's say you want to do a Hessian-based optimization methods, or let's say in the MCMC setting, you want to do true Riemannian manifold sampling. So the full Riemannian manifold does require the Hessian term, the Hessian of the posterior log density to construct proposal. And this is, in fact, something that we're looking into right now because of the work that Blake Christensen led at UT Austin. He's able to train a surrogate model using the second order derivative, and which give us a definitive way of enabling these, let's say, Riemannian manifold sampling. And this is something we're looking at right now.
Oh, awesome. And then a second question was that when you are collecting the training data for learning these derivatives and for getting the snapshots, do you observe if any sampling plans other than purely pseudo-random sampling for the parameters yields different results and as far as the quality of the surrogate model is concerned? Because it could be that maybe for some regions of the parameter space, the data snapshots that you generate are maybe not so diverse, and so the surrogate potentially doesn't generalize, or is that generally an issue?
Yes, it's always an issue for surrogate. So first of all, the surrogate, even though we're doing a function approximation, so if we were to go back to the first slides, the function approximation is expected over some distribution. So there's no guarantee that if you shift the distribution, it will actually do well. So that's actually a key problem in a lot of surrogate-driven applications. For inverse problem, for example, if you're given a data and the posterior is extremely localized, then is the surrogate error is gonna enlarged compared to your error measured in the training distribution. So the way to address this is think about two directions. The first direction is if we really care about a particular distribution, then we probably should train on that particular distribution. Uh, if we really care about region of a parameter space, then we should either generate data upfront or do it in an adaptive way to either directly train a surrogate or fine-tune the surrogate in those region. So that's my first answer. So the second point though is more subtle. So for inverse problem, for example, sometimes we don't know the data. We're expecting some data coming in. We don't know the data. So it's hard to say upfront, what kind of region of the parameter space should we target? So in that case, either you want to do it adaptively, after getting data, you invest some computation into tuning the model, or you just do a really accurate surrogate over the entire prior. So we know the prior distribution is on average the best for unknown data distribution because our best guess of what the system is um, should somehow cover hopefully cover in some way what the data look like. So the reason I'm saying this is because I'm going to go back to the error bounds that I'm showing you. So this error bounds is important because we're doing expected over data. We don't know the data yet. So in that sense, I think uh, simply doing a really good approximation over the prior is really helpful.
Okay. Yeah, thank you. That makes a lot of sense. Are there any other questions online or?
I'm sorry if I missed this, but how do you choose the points where you want to construct a surrogate? Is it through some greedy algorithm?
So the points that we consider right now is just sampling. So for inverse problem, it's very natural that we do have a prior distribution coming in. So mu here is a prior distribution, and we have a prior belief of where the system is. So as long as it will stay in there in this distribution, we are kind of safe in some sense. So in the setting that I'm interested in right now, we always come with a distribution that we sample from. Now, in terms of a greedy approach, or in terms of active learning of samples on input, this is something that there's a bunch of techniques out there that people can use. But one of the things that I thought very interesting is that if we do have a PD solution operator, if the structure of the PD is relevant, then we can say something about um, maybe something about the residual of the PD to be able to measure where the error is largest in the input space. But of course, that's beyond really the things that I'm talking about here. And in right now, we stay in the IID setting where we assume the data is independently sampled from a given. Yeah.
Sounds good. Thank you. Just one final question. So, the basis for your like reduced dimension as well, is that the same data you use for the surrogate construction, or is it different?
Exactly. So the basis that we use is used for the surrogate. So the procedure goes as follows. So we first generate input, output, and Fauché derivative samples, and we use some of the Fauché derivative sample to define the basis by solving eigenvalue problem. And that basis is now used as the input encoder and decoder to project the data and to construct the surrogate during the training. So that's what we do.
I see. That makes sense. Yeah. Thank you.
Okay. So if there are no other questions, let's just thank our speaker again for this wonderful talk.
Thank you.
Yeah. It was a pleasure to have you here, and to everyone else, we'll see you again in 2 weeks' time for the next seminar. Yeah. Thanks a lot for.
Thank you.